I think that you can see my screen.
Yeah.
Okay. Yes.
Okay, perfect.
Okay, great.
Can I start?
So let me introduce you quickly. We will have this first talk before the coffee break from Ludovica CESTARIOLO. She's a PhD student. I hope I do not mistake, from Politecnico di Milano.
Yes.
And she will present, give a talk about the electrophysiology of the zebrafish heart, a computational model.
Yes.
So Ludovica, the floor is yours.
Thank you. Good afternoon to everyone. Thanks for the presentation. I am Ludovica, and the title of my work is Electrophysiology of the Zebrafish Heart, a Computational Model. So recent studies suggest that the physiology of the zebrafish resembles that of humans in many aspects. Namely, it has similar spontaneous heart rate. The QT interval in electrocardiogram is heart rate dependent. It has similar action potential shape and duration, and it also shows the presence of orthologs of human ion channels. So for all this reason, it has been supposed that zebrafish could be a potential model for genetic and pharmacological screenings of factors that could affect the heart functions. Despite the rising interest in the last years in zebrafish, to date, few studies concern the development of a computational model. And so the aim of this work is to create a reliable computational model of the zebrafish heart, with the ultimate purpose of assessing the main electrophysiological parameters and their correlation with pathologies and drug administration. In this work, a full electrophysiological model of a 3 days post-fertilization zebrafish was developed. The heart of the zebrafish has a very simple structure. In fact, you can see in the figure that the zebrafish has a two-chambered heart that at the stage of 3 dPF is approximately 100 micrometers in size. And in this work, the geometry is based on the geometry reported in the work of Crocombe et al. And it is composed of 3 main parts: the body, the heart chambers, and the heart myocardium. The latter is in turn divided into 4 distinct regions, namely the sinoatrial region, that is the area where the stimulus is delivered. Then we have the atrial wall, the atrioventricular band, and the ventricular wall. In addition, you can see that the atrioventricular wall and the ventricular wall were divided in other subparts in order to recreate the heterogeneity in electric propagation. In particular, the atrioventricular band was split into 2 distinct rings, one on the atrium side named AV band 1 and one on the ventricle side named AV band 2. To these 2 parts were assigned different action potential model. In particular, to AV band 1 was assigned the action potential model of the atrium, and to AV band 2 was assigned the action potential model of the ventricle. The ventricular wall was then split into 3 parts, ventricle 1, 2, and 3, in order to recreate the apex to base activation pattern that we found in literature. The simulations in this work were set up in LS-DYNA with a bidomain model to model the electric propagation of the heart, while body was considered as a volume conductor. The model used a semi-implicit numerical scheme with a fixed time step of 0.02 milliseconds, and it was stimulated with 3 beats at a basic cycle length of 500 milliseconds. That corresponds to an heart frequency of 2 hertz, that is the normal range for the zebrafish. The heart tissue was considered as isotropic. We have different conductance values for the regions of the model, and these values were adjusted in order to fit the experimental data, and so to recreate the activation sequence and activation times from literature. Regarding the action potential model, in this work, the Bueno-Robbio for variables minimal model was used. This model allowed to recreate a large variety of action potential shape by using just 4 state variables. And in this work, it was adjusted in order to fit the experimental data for the action potential of the zebrafish. And in the graph, you can see the experimental and numerical action potential model for atrium and ventricle that were used in this work. So here are the results regarding the transmembrane potential. So you can see the activation sequence and times. In particular, the atrium activated in 36 milliseconds. Then there is a delay of about 14 milliseconds caused by the presence of the atrioventricular band. And finally, the ventricle activated in 59 milliseconds. and with an activation apex to base. These results were found to be in line with experimental data, especially they were compared with the work of Panakova that perform optical mapping for transmembrane potential. Regarding the action potential, we analyzed different characteristics of the action potential morphology, in particular in terms of action potential duration that was evaluated as the time interval between the peak and the 9% of repolarization. Then we evaluated the action potential amplitude and the maximum and minimum action potential derivative. Here are shown the results. Also in this case, the results were found to be in good agreement with the experimental data, except for the value of the upstroke velocity that you can see that is significantly higher with respect to the experimental value. But this could be related to the calibration process of the action potential model. Lastly, we obtained dipolar ECG that was computed between two electrodes that were located on the body in correspondence of the ventricular base for the positive electrode and to the ventricular apex for the negative electrode. Here is shown the ECG signal that is in line with the activation sequence that you saw before. In fact, the duration of the P wave and the QRS complex are in line with the duration of the activation of atrium and ventricle, respectively. It is worth noting that in the 3DPF zebrafish, the size of atrium and ventricle are quite the same. So for this reason, the amplitude of the P wave is very high. And also there is a small decrease after the QRS complex that lasts about 52 milliseconds. That represents the atrial repolarization. And finally, the T wave is a biphasic wave that is also in line with the depolarization-repolarization pattern of a 3DPF zebrafish. So to sum up, in this work, we developed a full electrophysiological model of zebrafish, heart plus body, that allowed us to obtain results in terms of activation sequence and activation times, different characteristics of the action potential morphology as the APD, IP amplitude, maximum and minimum action potential derivative, and also a dipolar ECG. The results are for now encouraging, but obviously this work is not exempt from limitations. And so the next step will be to incorporate the APD restitution curves to the action potential model in order to assess the changes in heart rhythm. And also it will be useful to create a model of a 4 or 5 DPF zebrafish, because at these stages, the heart rhythm is more stable. And also the volumes of atrium and ventricle are more similar to the adult fish. So thank you for your attention.
Okay, thank you very much for your talk. We are ahead of time, so if there are questions, we have plenty of time. And so maybe I will start with one, maybe two. The first one is so it's a curiosity. So right now, it's your work is really well aligned with data, with available data. So I think that you have done an excellent work of validation. And I was curious about then once you have validated also on other let's say on different on additional data, how you would then use this model maybe for predict some pathological behavior or something like that. So that is my first question. And the second one is related mainly to the propagation pattern. And so in your case, I've seen that there are no fibers or principal direction of conduction. And so my question is about the real anatomy of the heart, if there are fibers or not, and if you are trying to surrogate them by using different regions and so on.
Yes, so as you said, in this work, there are no fibers in the model. I can show you, okay. Yes, for now, we use this strategy of dividing the parts on the model to obtain the activation sequence, but obviously it will be great in future to use fibers. But I think that would be necessary to use a 4 or 5 days DPF zebrafish, because at this stage the heart is not yet formed, so it could be a little bit difficult.
Okay.
But in general, I think that for now there is a lot of work to do on calibration, also on the results of the activation times. But I think that this work will be concentrate on the ECG evaluation, and modifying the action potential model, we can perform different situations of pathologies, for example.
Okay, and are there available data on pathologies, or only on?
Yes, there are a lot of studies regarding adult zebrafish. It is quite difficult with embryos, but yes, with 5 days post-fertilization zebrafish, it will be more easier, because the heart is more similar to the adult fish. So yes, it can be done.
Perfect. So there is a question from Kerwar. So please open your microphone.
It's Carla.
Carla, okay, great. Sorry, because from your name, your Zoom name, it was not clear.
Oh, okay. Yeah, it's my iPad. Sorry. Yeah, I'm just wondering, how much do you think this will speed up simulations when incorporated in, like, at an organ scale simulation?
Sorry, I don't hear you very well. Can you please repeat?
Yeah, I said at one point, like, by how much do you think your simplified model of the zebrafish would improve organ scale simulations?
Yes, this is a very simplified model, but as I said in the beginning, the zebrafish has a particular characteristic that are more similar to those of humans than, for example, other mammals like rats or pigs that are usually used in animal trial. And also the particularity of this animal is that has a very high fertility, so you can have a large amount of eggs in just 1 week. And so this allowed for statistical analysis in vivo trial. And so I think that it could be useful for analyze the human aspect, because it is very similar aspect. It has very similar characteristic.
Thank you. Yeah, super cool stuff.
Thank you.
So thank you, Carla. And there is another raised hand from.
Yeah, I'm here.
Okay, perfect.
Yeah, I'm sorry I didn't manage to change my real name. So my name is Karim, and well, you recognized me, Ludovica.
Yes, hi, Karim.
Hi, it's very impressive. Thank you for the talk, and it's amazing to see how much progress you've made in very few months. So first question is, how would you incorporate restitution curves into the model, and what kind of data would you use for that? And the second question would be, in order to have a cleaner ECG, do you intend to see if there is a parameter identification step that could be useful, meaning on ionic model parameters, in order to incorporate heterogeneity, etc., and what parameters would that be? And also, what's the final application for the pharma world with this whole modeling thing?
Okay.
Thank you.
I start with the ECG. Right now the ECG have some issues. For example, there is a decrease in the middle of the P wave that could be, for example, related to the activation of the atrioventricular band. These are preliminary results, but according to the timing, we think that this is the activation of the atrioventricular band. So maybe with a better calibration of the conductance values for now, it will be possible to obtain a more clean signal. And also with the modeling of a 4 or 5 days TPF zebrafish, this decrease, for example, due to the fact that the atrium is smaller with respect to the ventricle at that stage, maybe this decrease would not present in the ECG.
Yeah, I will be part of the second.
And the other question, I don't remember, sorry.
Yeah, sorry, it was a bit long. The second question was, how would you incorporate the restitution curves into the model, and what data
Yes.
would you use for?
Yes, we have a code for fitting the experimental data with the Buono-Rovio model. And in this model, it is possible to obtain different action potential shape with respect to the basic cycle length that you select. So in this way, the restitution curves, we obtained the restitution curve from the experimental data that we found in literature, and then we can create the action potential model for all the APD that you want.
Okay, so basically the input would be the restitution curve, and the output would be an action potential.
Yes.
Optimized action potential.
Yes, the Buono-Rovio model used the restitution curves to obtain different action potential model.
All right, thank you.
Okay, perfect. So I would like to, so if there are no additional questions, I would like to thank Ludovica for her talk.